In this video, I'm going to talk about Hamiltonian graphs and its connection to biconnected graphs. So first, several definitions. So Hamiltonian cycle in a graph is a cycle that passes through all vertices of the graph. Then a graph is said to be Hamiltonian if it has a Hamiltonian cycle. And so then a biconnected graph. So a graph is said to be biconnected if it is connected and if removing any of the vertices still doesn't violate its connectedness. So if it's connected, and if after a removal of any vertex it still remains to be connected. So, and the main theorem that I'm going to discuss in this video is that Hamiltonian graph is biconnected, but the converse is not true. So it could be that the graph is biconnected, but it's not Hamiltonian. So let's consider the proof. So the proof first. Let's consider the proof in this direction. So we suppose that it's Hamiltonian, and we need to prove that it is biconnected. So suppose it is Hamiltonian. So we need to prove that it is connected, that it is biconnected. So well, if it's Hamiltonian, then there is a cycle that passes through all vertices. So essentially, a graph looks like this. All the vertices are on these graphs, and there could be some additional edges like this, but it doesn't matter. We are not concerned about these edges. So what is important is that let's not erase them. So there are some edges like this, but what is important is that there is this cycle that passes through all vertices. So now first we observe that it is connected, because any two vertices, like vertex here and vertex here, we can go through from this vertex to this vertex along this cycle. We go from here to here, therefore it is connected for any two vertices. So why is it biconnected? Well, if we remove any vertex, let's say there is a vertex here, we remove it. Okay, so but then we still can go. There is still a Hamiltonian path. It's not a cycle anymore, but it is a. Yeah, so it's not a cycle anymore, but it's still a path. So we still can go through all vertices in this path. So from this vertex to this vertex, we can go along this path regardless of the removed vertex. Okay, so it is biconnected. So this basically concludes the proof in this direction. So now the proof in the other direction. So well, not the proof, but a counterexample, like the statement that the converse is not true. So a counter example would be the Peterson graph. So a counter example is the Peterson graph. So the Peterson graph, it looks like this. There is so it has 10 vertices and 15 edges. So there is a external pentagon, there is internal pentagon, and there are crossing edges that connect the external pentagon to the internal pentagon. So so it has 10 vertices, 15 edges, and the degree of each vertex is 3. So it's 3 regular. So first we observed that it is biconnected. So it is biconnected. Well, this is like we can observe it directly. Like if we remove any vertex on the external, like we notice that the graph is symmetrical. Like so, up to rotation, we can like we need to consider only 2 vertices. So first, if we remove any vertex on the external pentagon, like we can, without loss of generality, we can remove any of them. Like let's say that we remove this vertex. Then we directly observe that the remaining of the graph is still connected. So, and by the symmetry, so like if we remove like by the symmetry, like because of the rotation symmetry, like all other external vertices are the same. We need to consider only one of them, and the same for the internal vertex. So like all of them are symmetrical up to rotation. So if we remove, let's say, this vertex, we observe that the remaining of the graph is still connected. Yeah, so it is biconnected. Now, why is it not Hamiltonian? So the fact that it's not Hamiltonian is a little more difficult to prove, but like I proved it in a separate video. So like literally the previous video that I published on this channel is specifically to prove that the Peterson graph is not Hamiltonian. So I refer you to this video. Yeah, so with these two properties, the properties that it's biconnected and not Hamiltonian, it proves that the converse statement is not true. So this concludes the proof of the theorem.